Hello students, in the previous lecture we see the solution of the differential equation, that is general solution and the particular solution, and the methods of the solving the differential equation, that is the variable separable method. Okay, we separate the variable, integrate it, and we get the solution of the differential equation. Okay, but in case of we cannot be separate the variables, then we reduce the differential equation in the variable separable form by using the substitution. Okay, it is the second method of the solving the differential equation. Now we see the third method of the solving the differential equation, that is the solve the homogeneous differential equation. Okay, first we see the homogeneous differential equation and then the method of the solving homogeneous differential equation. Here the homogeneous equation, we are very well known the homogeneous equation in a pair of straight line chapter. Okay, there is the combined equation of two lines passing through origin represent the second degree homogeneous equation. The second degree homogeneous equation. Here for the example we see it is a 3x square plus 4xy minus 5y square is equal to 0. Here it is a second degree homogeneous equation. Homogeneous equation means the degree of the each term in the equation is same, and degree of the term means the sum of the powers of the variables. Here it is a second degree equation in a x and y. Okay, second degree homogeneous equation in x and y. Here the sum of the powers of x and y, sum of the powers of x and y, and it is the sum of the powers of x and y are the same. Okay, here it is a sum of the powers of x and y. Here the power of the x it is 1, power of the y it is 1, and sum is a 2. Here power of x is 2 and here y is absent, that means the power of y is a 0. Okay, y to the power 0, that means 1, it is only, we can write x square. Here the power of x, sum of the powers of the x and y, variable x and y is the same. It is a homogeneous equation. Okay, here we know it is a second degree homogeneous equation. Okay, second degree homogeneous equation. Now the homogeneous function, okay, here it is second degree equation in a x and y. Now we can write only the homogeneous function. It is f of x comma y. It is 3x square plus 4xy minus 5y square equal to 0. It is a homogeneous function. It is an equation, equality between two quantities. Here it is equal to, here it is a homogeneous function, and the definition of the homogeneous function, see carefully this, it is f of, okay, lambda into x comma lambda into y is equal to, here lambda to the power n, here we can write lambda to the power n f of x comma y. Here lambda is a non-zero scalar, that means it is a homogeneous function, form of the homogeneous function. Okay, now here we see this example. Okay, now we can write it is a f of lambda x into lambda y. Then replace x by, it is a function. Okay, here our function, homogeneous function, it is a 3x square plus 4xy minus 5y square. Replace x by lambda x and replace y by lambda y. Then we can write 3 into lambda x square plus 4 into lambda x into lambda y and minus 5 into lambda y whole square. See carefully this, and then it is a 3 into lambda square x, 3 into lambda square x square, 4 into lambda square xy minus 5 into lambda square y square. Then this can be written as lambda square, take common, 3x square plus 4xy minus 5y square. Now here this can be written as it is lambda square into f of x comma y. See carefully this, it is a f of x comma y. That means here it is the homogeneous function in x and y of degree 2. It is homogeneous function in x and y of degree 2. It is the definition of the homogeneous function. Okay, here in case of, here it is, we can write f of x comma y is equal to tan of x comma y. So it is tan of y by x or x by y. Okay, is also the homogeneous function. See carefully. When we can write, it is lambda x into lambda y, then it is tan of lambda y upon lambda x. Then this lambda get cancelled, then we can write tan of y by x, but here into 1, this can be written as it is a lambda to the power 0. That means it is homogeneous function of degree 0. Homogeneous function of degree 0. It is a tan of y by x. When we replace x by lambda x and y by lambda y, then we get this. It is lambda to the power 0 f of x comma y is also the homogeneous function. Okay, tan of y by x or x by y. Now it is a homogeneous function. It is f of lambda x into lambda y is equal to lambda to the power n f of xy. It is a homogeneous function of degree n. Okay, it is homogeneous function of degree 2. It is homogeneous function of degree 2 in x and y. Okay, it is a homogeneous equation. Okay, homogeneous equation of degree 2, homogeneous function of degree 3. Okay, here for example we can write f of x comma y, it is x cube plus 4x square y minus xy square plus 2y cube. It is homogeneous function of degree 2. Okay, we can check like this: x replaced by lambda x and y replaced by lambda y, then we get lambda to the power 3. It is f of lambda x into lambda y, then we get lambda to the power 3 f of x comma y. It is f of x comma y. Okay, like this, lambda x into lambda y. Replace x by lambda x and replace y by lambda y, then we get this. That means this is homogeneous function of degree 3. It is a homogeneous function of degree 2. But in this lecture we see the homogeneous differential equation. Okay, here it is a homogeneous function. Okay, f of x comma y, it is a homogeneous function. F of x comma y is a homogeneous function, but we see the homogeneous differential equation. Now what is the differential equation? An equation which contains the derivatives of the function is called the differential equation. Here it is only the second degree equation. Okay, here it is second degree homogeneous equation in x and y. But now we see the second degree homogeneous equation. Okay, sorry, second degree homogeneous differential equation. Okay, here differential equation is an equation which contains the derivative of the function. It's called the differential equation, that is dy by dx or dx by dy. Here we can write here dy by dx. Now here this equation is a homogeneous differential equation of degree 2. Okay, first we write it is 3x square plus 4xy minus 5y square equal to 0. It is only the second degree homogeneous equation. But here now in this equation there is a derivatives dy by dx. Therefore it is a differential equation, and here it is a homogeneous differential equation because the degree of each term is the same. Okay, now the form of the differential equation. Okay, here the form of the differential equation, here it is a dy by dx is equal to f of x comma y upon g of x comma y. Here f of x comma y and g of x comma y are the homogeneous function of the same degree. Okay, form of the differential equation we can write this, or we can write also this dx by dy. It is f of x comma y, g of x comma y. Here we can write any one form of the differential equation like that, okay, which is easy to write, or for the solving the example it is a dy by dx or dx by dy. But here f of x comma y upon g of x comma y, here f of x comma y and g of x comma y are the homogeneous functions of same degree, okay. Here f of x comma y and g of x comma y are the homogeneous function of same degree. Okay. Then it is called the homogeneous differential equation, and the form of the homogeneous differential equation, it is a dy by dx is equal to f of x comma y upon g of x comma y. Both are the homogeneous functions of same degree. Now see this example. We can write this is a homogeneous differential equation. We write this homogeneous differential equation in the form of the homogeneous differential equation here. Therefore we can write it is a minus 5y square dy by dx. We can write in a RHS. Therefore it is a 3x square plus 4xy is equal to 5y square dy by dx, and therefore dy by dx is equal to 3x square plus 4xy upon 5y square. Here it is a form of the homogeneous differential equation. Here it is f of x comma y, it is a homogeneous function in x and y. It is also homogeneous function in x and y of degree 2. Here it is a second degree homogeneous function, and it is also in the denominator is also second degree homogeneous function. Here see carefully, this is the form of the homogeneous equation. dy by dx is equal to f of x comma y upon g of x comma y. Here f of x comma y and g of x comma y are the homogeneous function of same degree. We can write dy by dx, or it is dx by dy. Okay, this function we can also write dx by dy. Therefore dx by dy, it is a 5y square upon 3x square plus 4xy. Okay, here it is a dx by dy. Okay, it is a homogeneous differential equation. And now here, how to solve the homogeneous differential equation, because it is not in the variable separable form. Okay, here it is a definition of the homogeneous function. So it is a homogeneous differential equation. It is homogeneous differential equation. See carefully this. Now how to solve the homogeneous differential equation? Here for substituting, if we write the differential equation here, see carefully, homogeneous differential equation in the form dy by dx is equal to this f of x comma y upon g of x comma y. When we write dy by dx, then by putting y by x is equal to v. See carefully, we substitute the another variable v. Y by x is equal to v. Here we reduce this equation in the variable separable form by using the substitution. But in the last lecture we see the reduce the variable separable form, the differential equation, by using the substitution. There is a clearly we write the function in the form of the composite function. Okay, and then we see which function we substitute. But here it is a 3x square plus 4xy upon 5y square. Okay. Here it is a homogeneous differential equation, and for the homogeneous differential equation we put y by x is equal to v. Okay, when we put y by x is equal to v, then differentiate, then we get the variable in the x and v. Here when we put y by x is equal to v, then this can be written as y is equal to xv. Okay, it is easy to differentiate than this. Here y by x, that means here we use the differentiate derivative u by v, but it is y is equal to xv. Here we use the derivative of u into v, and u into v is easy than the u by v. Okay, now here put y by x is equal to v, that means y is equal to xv. then we find the value of dy by dx, and then put the value of dy by dx is here, and here put the y is equal to xv. Then now our new variables are the x and y, x and v, and then we separate this. Okay. After substituting, we get the variable separable form in the variable it is v and x. We separate the variable and integrate and solve it. Okay. Here substitution clearly. See carefully, it is a y by x is equal to v when we write dy by dx, when the homogeneous differential equation in the form. Okay, it is one method. And the second, when we write the differential equation in the form, it is f of x comma y, it is f of x comma y is any function, and it is a g of x comma y is any function. Okay, it is a homogeneous function and it is also homogeneous function. If we write dx by dy, then we put x by y is equal to v. Here it is a dx by dy and here it is a dy by dx. Okay, we can both methods apply. Here we write dy by dx, but it is easy to write the dy by dx, so we generally use the dy by dx, that means the substitution y by x. Okay, but some problems when we write the dy by dx, it is difficult to solve, so we convert this into dx by dy and solve. Okay, when we write this dx by dy, then put x by y is equal to v, that means x is equal to y into v, and then find the, after differentiating, here it is a differentiate with respect to y, here differentiate with respect to y, then it is dx by dy is equal to derivative of, it is y as it is, derivative of phi with respect to y, and plus phi as it is, derivative of y, it is 1, and here differentiate with respect to x, differentiate with respect to x, because y is equal to x phi. Here we want dy by dx, so differentiate with respect to x. Here we want dx by dy, so differentiate with respect to y. Okay, these are the two methods for solving the homogeneous differential equation. See carefully. Okay, these are the two methods. When we write the homogeneous differential equation in the form of the dy by dx, we put y by x is equal to v. Here dy by dx, it is y by x. Put y by x is equal to v. When we write the differential equation in the form of dx by dy, then we put x by y is equal to v, and then differentiate with respect to y. Okay, and then after substituting, there are the new variables y and v. We separate this variable in this form. New variables are x and v, and then we solve this differential equation by using the variable separable form. Now these are the homogeneous differential equation. Here it is a homogeneous differential equation. See carefully this. Okay, now we see some examples of the homogeneous equation. Solve the following differential equation that are in the form of the homogeneous differential equation. Now we see the examples in the exercise 6.4. Solve the following differential equation. Okay. There is a not question asked in the form of the solve the following homogeneous differential equation. The question asked is only the solve the following differential equation. We identify it is a variable separable form, or reduce the variable separable form of it, or the homogeneous differential equation. Okay. Now here the given differential equation, given differential equation is this differential equation, x into sine of y by x dy is equal to y into sine of y by x minus x dx. To solve this differential equation, first we write in the form of the dy by dx and check this it is a homogeneous form or not. Okay, here we write the dy by dx. See carefully, it is a dy and it is a dx. Therefore this equation becomes dy by dx is equal to y into sine y by x minus x upon x into sine y by x. Okay, now here it is a form of the dy by dx is equal to, now the form of the homogeneous differential equation, it is a dy by dx is equal to f of x comma y upon g of x comma y. See carefully this, and both are the homogeneous functions of same degree. Okay, f of x comma y and g of x comma y are the both homogeneous function. Now in this example here we see f of x comma y is equal to y into sine of y by x minus x. First we check this, it is a homogeneous or not. So we put it is a lambda x and lambda y, f of lambda x into f of lambda y. Definition of the homogeneous function, it is f of lambda x into lambda y is equal to lambda to the power n f of x comma y. Here it is a homogeneous function of degree n. Now here x replaced by lambda x and y replaced by the lambda y, then we get lambda y into sine of lambda y upon lambda x and minus lambda x. Then here this lambda get cancelled, y by x, and here lambda and this lambda we take lambda common, then we get y into sine y by x minus x, and here it is lambda into f of x comma y. That means it is lambda x and it is lambda y. Okay, here lambda f of x comma y, that means lambda to the power 1, that means it is a homogeneous equation, sorry, it is a homogeneous function in degree 1. It is a homogeneous function of degree 1. Okay, it is f of x. So we can check the g of x. Okay, here we write g of x comma y, and g of x comma y, it is x into sine of y by x. Then g of lambda x into lambda y is equal to lambda x into sine of lambda y by lambda x, and again it is lambda into x sine y by x. This lambda get cancelled and it is lambda, and then it is lambda f of, sorry, here g of x comma y. That means g of x comma y is a homogeneous function of degree 1. f of x comma y is a homogeneous function of degree 1. That means it is a homogeneous differential equation of degree 1. It is homogeneous differential equation of degree 1. Now here we write the dy by dx. So put y by x is equal to v. Okay, here we first check this homogeneous differential equation or not, or the solution of this differential equation can also solve by the last method or reduce the variable separable form. Here our standard function, it is a sine x is a function of x, or sine y, it is a function of y, but it is a sine of y by x, that means sine of x comma y. Here in the angle there is a y by x, two variables, so we reduce these two variables in the one variable by using the substitution. That means here we put y by x is equal to u or v. We can solve this example also by the last method, that is the reduce the following equation in the variable separable form. Okay, now here it is a homogeneous differential equation. Put y by x is equal to, put y by x is equal to v. Therefore y is equal to x into v. Okay. Now differentiate with respect to x. Then we get dy by dx is equal to, first as it is, derivative of the second, plus second as it is, and the derivative of the first, it is 1. Okay, it is equation number 1. Now the equation 1 becomes dy by dx, it is dy by dx, x into dv by dx plus v is equal to, see carefully this, here y is equal to xv into sin v y by x minus x upon x into sin v. See carefully this. Now we can take common this x, and therefore we get x into dv by dx plus v is equal to, here v into sin v minus 1 upon only sin v. Okay. Now it is a dv by dx. Now this differential equation we can solve by using the variable separable form. Here it is a v plus v, we can write in the minus v. Therefore x into dv by dx is equal to v into sin v minus 1 upon sin v minus v. Here this plus v we can write in the RHS, it is a minus v. Then they calculate. Therefore we can write x dv by dx is equal to v sin v minus 1 minus v into sin v upon sin v. See carefully this. It is a multiplication of sin v into v, and here v sin v, and it is a minus v sin v, get cancelled. We get only minus 1 upon sin v. Here now it is x dv by dx. Separate the differential coefficient, that is x into dv is equal to minus 1 by sin v into dx. This dv and dx are the differential coefficient. We separate the differential coefficient. Now take the all terms of the x with dx and all terms of the v with dv, and therefore it is a sin v dv is equal to minus 1 by x dx. This x in the multiplication we write in the division, sin v in the division we write in the multiplication. Now taking integral on both sides, it is a variable separable. Taking integrals, therefore it is a sin v dv is equal to minus 1 by x dx, and integral of sin v with respect to v, it is a minus cos v is equal to minus log x and plus c. This log x we can write here. Therefore log x minus cos v is equal to c. Put the value of phi. Therefore log x minus cos of y by x is equal to c is general solution of given differential equation. Okay, see carefully. Log x minus cos y by x is equal to c. It is a general solution of this differential equation. Okay. Now we see the next example. See carefully this. It is in the form of the homogeneous differential equation, and here we write the dy by dx. So we put y by x. If we write dx by dy, then we put x by y. Now the second example. x square plus y square dx minus 2xy dy is equal to 0. Okay. Here, the given differential equation x square plus y square dx minus 2xy dy is equal to 0. Here, clearly in this equation there are the three terms, x square into dx, y square into dx, and 2xy dy. And here the x square, y square, and 2 into xy, the degree of all three terms is the same. That means it is a second degree homogeneous equation, and there are the differential coefficient. Therefore, it is a second degree homogeneous differential equation. Okay. Now we write this equation in the form of the dy by dx. Therefore, it is x square plus y square dx is equal to 2xy dy. We write this equation in the form of the dy by dx. So this dx becomes here and 2xy becomes in the denominator. Therefore, dy by dx is equal to x square plus y square upon 2xy. It is equation number 1. And here it is our homogeneous differential equation. Degree of the numerator, degree of the function in the numerator, it is x square plus y square. It is 2, same. And here in the denominator again it is x plus, it is degree power of x, it is 1, and power of y, it is 1. So the degree of the function in numerator and degree of the function in the denominator is the same. That means it is a homogeneous functions. Okay, numerator and denominator of same degree. Here we can write the dy by dx. So put y by x is equal to phi. Put y by x is equal to phi. Therefore, y is equal to phi x. Then differentiate with respect to x. Therefore, we get dy by dx is equal to, it is phi into derivative of x, it is 1, and plus x into derivative of phi. Okay. Here, put dy by dx in equation number 1. Therefore, equation 1 becomes dy by dx, it is phi plus x into dv by dx is equal to x square plus phi square x square. It is a value of y. X square plus y square. Y it is a vx, and 2x into x phi. And here x square take common, and in the denominator there is x square, get cancelled. We get 1 plus phi square upon 2v. See carefully this. X square take common, and it is a x square, get cancelled. Here only 1 plus phi square, and it is a 2v. It is the remaining. Now phi plus x dv by dx, this can be written as x into dv by dx is equal to 1 plus phi square upon 2v minus phi. This plus v we can write here, and therefore it is 1 plus phi square minus 2v square upon 2v. See carefully this. X dv by dx is equal to 1 plus v square, and it is 2v minus v. It is minus v square. Therefore, it is x into dv by dx is equal to 1 minus v square, 1 minus v square, and upon 2v. 1 minus v square upon 2v as it is. Okay, see carefully this. Now, it is a dv by dx. It is a differential equation in the variable v and x. In the variable separable form, first we separate the differential coefficient, that is the dv and dx. Okay, and then separate the all variables. Therefore, x into dv is equal to 1 minus v square upon 2v into dx. Differential coefficients are the separate. Now take the all variables of x with dx and all variables of phi with dv. Therefore we can write 2 phi upon 1 minus phi square dv is equal to 1 by phi it is 1 by x dx. This 1 by x. Now the variables are the separated, then taking integral on both sides. Therefore integral 2 phi upon 1 minus phi square dv is equal to integral of 1 by x dx. Now it is 1 by x, it is a log x, but here 2 phi upon 1 minus phi square, it is a linear function upon the quadratic function. That means we adjust the derivative of quadratic function in the linear function, but here clearly the derivative of 1 minus phi square, it is a minus 2 phi. So we can write here minus 2 phi upon 1 minus phi square. Here the derivative of 1 minus phi square, it is a minus 2 phi, but here it is a plus 2 phi. So we multiply the minus. This dv is equal to integral of 1 by x dx. Okay, see carefully this. Now here it is minus and f dash of x upon f of x. Therefore the integral, it is a log of 1 minus phi square. Okay, you know the rules of the integration. Here it is a integral of f dash of x upon f of x with respect to x, it is a log of f of x. Here f dash of phi upon f of phi with respect to phi, it is a log of f of phi. Here is equal to log x, and both integrals are in the log, so constant is also in the log. Okay, see carefully this. Now removing log on both sides, so we can write it is a minus. Okay, therefore we can write it is a log 1 upon 1 minus phi square, take the reciprocal of this, okay, minus is equal to log x into c, removing log on both sides. Therefore we get 1 upon 1 minus phi square is equal to x into c. Now put the value of this phi, okay, then 1 upon 1 minus y square by x square is equal to x into c. Therefore, okay, we can write x square upon x square minus y square is equal to x into c. See carefully this. Here x square minus y square, in the numerator x square, then this x gets cancelled, we get it is x upon x square minus y square is equal to c, is general solution of the differential equation. Is general solution of the differential equation. X upon x square minus y square is equal to c. Okay, see carefully, it is a homogeneous differential equation. We write this homogeneous differential equation in the form of the dy by dx. Here we write the dy by dx, so put y by x is equal to phi. When we write dx by dy, then here put x by y is equal to phi. See carefully this example.